holiday because you don't have to cook for everyone. You don't have family going everywhere. You just go and have fun. Okay. We are recording. My audio is good. Okay, so a couple of things. Last class we finished up and we were talking about arc length, right? And we proved that the circumference of a circle is 2 pi r. That's where we stopped, right? Anybody that wasn't here that didn't get the formulas from last time? Okay. All right, so now I have another handout for you, which has some formulas for arc length on it. And that's what you see up here. So I'm just going to take this stack and pass it around. Just take one and let's get that all the way around. So to start off, we're going to do a couple of more examples with arc length, and then we're going to move on to surface area. So I want to try and remind you that last time, when we came up with that arc length formula, what I did was we took a function, right? We said, okay, we want to find the length of that little piece, so we zoomed in on it. Does this look familiar? Yeah. Then we drew a right triangle in here. We called this dx, we called this dy, right? And then we called this side that we're trying to find L, and we said that L squared was equal to dx squared plus dy squared, right? And then we solved for L by taking the square root, and we got dx squared plus dy squared. And at this point I said, okay, well if this is the length that we're trying to find, that we just need to add them all up, and so we created an integral from this. And the problem was that if we just put this right here in the integral, we didn't have like a dx on the outside. So do y'all remember what I did at this point? I factored out a dx squared from here, in here. Well, when I did that, let me put it up here. When I did that, what we got was this. That L was equal to, we pulled the dx squared out, and it came out of the square root as a dx, because we took the square root of something squared. Then inside we had 1 plus, the 1 is when we pulled out dx squared from here, and then this one, since there wasn't a dx squared, we had to divide by dx squared, which gave us this dy dx squared. So that was the formula that we used last class, right? I decided to pull out dx squared, but I could have pulled out dy squared instead, right? I mean, why not? So if I pull out dy squared instead, what I'll have is L equals square root, I'll have a dy out here, right? And instead of having a 1 here, I'm going to have dx over dy squared and then plus 1 over here. So the difference between these two approaches is that this right here would mean y prime, right? Which would mean that we would need to take the derivative of our f function with respect to x. That would be if our curve f was a function of x, right? This formula would work if we had, this really means like x prime, which is not 1. And this would mean, well, if we had a curve that looked like this, where it was not a function of x, but instead a function of y. Okay, so I'm going to use g instead of f. So it's not a function of x, but it's a function of y. Then this would work because this would be g prime of y. Does that make sense? So at the end of the day, we have two expressions for L, right? We have this expression for L and this expression for L, and they're equivalent. You can use either one, all right? So in the notes, everyone have the notes I just passed out? In the notes, what you're going to see here is that we now have two formulas for arc length, and which one you use depends on the actual curve or function that you're given. Okay, so if we have a function of x, we're going to want to use this one, right? And we'll have a dx out here, and this will be the derivative of f with respect to x. But if we have a function of y, we'll use this one instead. They will give you this, they will yield the same results, okay? Now, because this piece and this piece are identical, since this and this are identical, we will now have a new notation for that piece. This right here with the dy or this with the dx, we will call this ds from here on out. And it's kind of weird, but this right here that's the variable that we use for arc length. Don't ask me why, okay? That's what we use for arc length in mathematics. So whenever you see something like we want to do an integral with respect to s, just that right there, that means arc length. Does that make sense? Because this means you're either doing this or this in the integral, and both of those are arc length, okay? Anybody going to take Cal 3? If you take Cal 3, you'll see that this little d whatever this is very important, because like in Cal 3, this will be ds, or sometimes d capital S, which means you're integrating with respect to surface area, or if it's d with sometimes you can integrate with respect to a vector. So I mean, that little s there after the d, or whatever that variable is, means something, all right? Okay, this thing is way too close to me. All right, let's do a couple of examples. Hopefully you'll see how this works out, and then we'll move on to surface area. So the first one I'm going to do, I'm actually working out of 7.4. I want to do y equals, so I'm doing a problem that you're not assigned for homework, okay? Let's look at y equals 1/4 x squared minus 1/2 natural log x, and x is between 1 and 2. So we want to find the length of this. All right, we want to find the length of that. Now, just for fun, let's graph it. Okay, I just want to see, just so we can see what it looks like. So I'm going to go to this Desmos graphing thing, and it was 1/4 x squared minus 1/2 natural log x. Okay, and we are looking at this curve between 1 and 2, right? So if we look at this over here, here's our x and y axes, and we're trying to find the length of this curve between 1 and 2. So that right there, that's what we want. Okay, how long is that curve? Understand? Okay. So how are we going to go about this? Well, we have to decide which of the two formulas we're going to use, right? So this is solved for y, right? Since it's solved for y, we could look at this as being a function of x, right? So we're probably going to want to use that first one. So I want to use that the length of this arc will be equal to the integral from a to b of the square root of 1 plus the derivative of f, whatever that is, squared dx. So we're integrating with respect to x, right? So we need a derivative now, right? Okay, so our derivative, well, it's Cal 1 now. So what's my derivative there? 1/2 x, okay, minus 1/2 times 1 over x, right? Derivative of natural log of x, 1 over x. So I'm going to write that as 1 over 2x. Is that all right? So this x is in the denominator, this x is in the numerator, right? Technically. All right, so that's my derivative, pretty clean. Now I'm supposed to square it, right? So I'm doing, this is all scratch work. I'm going to do the integral in a second, right? When I square this function, the derivative, I have to multiply this times itself, right? and then I just like FOIL it out, right? So let's see what we get when we multiply this out. So this first multiplication, what do I get there? 1/4 x squared, or x squared, 1/4 x squared. Okay, now look at the middle terms. This is kind of interesting what happens here. You're doing 1/2 x times negative 1/2x. The x's cancel, and the halves, they multiply, don't they? So that just gives you negative 1/4. And then we'll have the same thing on the inside, won't we? The x's cancel, so we get minus 1/4 again. And then the last one, here to here, it'll be a plus, won't it? Because they're both negative, plus, and then just multiply the fraction straight across. 1 times 1, and then 2x times 2x, 4x squared. Now this becomes 1/4 x squared minus a half plus 1/4x squared. And that's just putting the minus 1/4 and minus 1/4 together to give you the minus 1/2, right? We win. That reminds me to turn mine off. Y'all good up to there? We good? Yeah. Okay, so now in the integral, we're supposed to add 1 to that, right? So if we look at this right now, if I add 1, things are actually going to be pretty nice, aren't they? Because all it will do is change that to a positive 1/2. Agreed? Okay, so let's go ahead and do the integral now. So this integral is going to be the integral from where to where. So what are my limits of integration? 1 and 2. And that was given to me, right? So I'm going to go from 1 to 2. And then the square root of 1 plus this, which I'm just going to do in my head. So that's 1/4 x squared, then it's plus a half, and then it's plus 1/4x squared, and then dx. All right? So whatever that answer is the length of this curve. Now, you know how I told you on your test you're going to have to, yes? What happened to what?
The 4 that was in front of x squared when you divided?
The 2 came down,
Oh, and
right? The 2 came down and made it a half. So the volumes where you wrap around the axes, I told you you're just going to have to set up the integrals, right? On these, when you get to the test, I'm going to tell you that you have to set up the integral, but you have to fully simplify the integrand. Okay, that means you have to fully simplify this. So this would not be what I would accept on the test as an answer. All right? And that's because all of these problems are made very special by the author of the book. And whoever wants to come up with an arc length problem, they have to be very careful that if they want you to take it all the way, that you can actually integrate this. So, you know, this is kind of a weird looking function, right? It was chosen this way because it will simplify very cleanly. This will simplify. We just have to kind of force it to happen, all right? So what I'm going to do here is I'm going to get a common denominator between all of these, all right? So just imagine that that's really x squared over 4 plus 1/2 plus 1/4x squared. So what would be a common denominator between those? 4x squared? 4x squared? Right? So I need to multiply top and bottom of this one by x squared. So I multiply x squared up here, x squared down here. What do I have to multiply this by on top and bottom? 2x squared on the top and bottom, right? And then what about this one? 1. So nothing. I don't need to touch that one, right? That one's okay. So let's see where we are here with this integral. We should be integral 1 to 2, square root. Okay. What's my new numerator? X to the 4th plus 2x squared plus 1 over my common denominator, 4x squared dx. Now, part of the reason why we want to get a common denominator is because if you get one fraction, right, one fraction, then you can do the root on the top and bottom separately, can't you? Yeah. But there's something even more, I was going to say more nice, that's not right. There's something even nicer, okay, happening up in the numerator. Do you recognize that we can do something with that? It's a quadratic type. It's not exactly quadratic because it's fourth degree, but it looks like a quadratic trinomial, doesn't it? And the question would be, does it factor? And it does, right? So we have to recognize that x to the fourth plus 2x squared plus 1 factors to be x squared plus 1 squared. So if you take x squared plus 1 and you multiply it times itself, you would get this. And that's what I mean by the problems are made very nice for you, because at the next step, if I have x squared plus 1 on top, but then squared, and on the bottom I have 4x squared, then I can take the root of the top and bottom separately. Dx equals integral 1 to 2. So the root of the top is just what? X squared plus 1. And then the root of the bottom is 2x dx. And then how would we do that? Split that up into two separate terms, right? Because we have two terms on top and one on the bottom. So this becomes integral 1 to 2. We've got x squared over 2x, right? Which is really just x over 2. So I'm going to write that as 1/2 x. That's the same as x over 2. And then this one, I have 1 over this, right? So I'm going to write that as plus 1/2, and then I still have an x on the bottom, right? But I'm going to write it as 1 over x out here. And the only reason I did that is because I'm taking an antiderivative. So the antiderivative 1 over x is natural log x, and the 1/2 will just come for the ride, right? So you all agree we're there? Yes? Yeah? You went like that. You went. You all right? Okay. So now, antiderivative of this. So just ignore the 1/2 right now. Antiderivative of x is 1/2 x squared, right? But you had a half out there. So 1/4 x squared. And then plus the 1/2 comes down. Natural log x. We're evaluating this from 1 to 2. And notice I did not put the absolute value on the x. The only reason I didn't do that is because my x's are going to vary from 1 to 2, right? So they're not negative, so I don't have to worry about like taking the absolute value of something that's already positive. And now we plug in. So if we plug in, let's see what we get. Plug in 2 first. So what happens when we plug in 2 here? We get 1 plus 1/2 natural log of 2, right? So we're plugging in 2 here and 2 there. And then we say minus, now we plug in 1. So when we plug in 1, we get 1/4 here, and then plus 1/2 natural log of 1. But what's natural log of 1? 0. So that's gone. So all you're left with is 1 plus 1/2 natural log of 2 minus 1/4. So this is really 3/4. It's 1 minus 1/4 plus natural log of, I didn't forget the 1/2. Natural log of, close, square root of 2. Because this 1/2 can go up as a power, right? Because property of logs. And raising something to the 1/2 is the same as taking the square root of it. Right? Okay, so this is it right here. So that's the exact length of that curve. It's the exact length. Now, if you wanted to approximate that length, you would just get your calculator out and get some decimal answer, right? Understand? Okay, so you can see that in this problem we had to do some algebra after we set up the integral to combine everything together so that we could take the root and actually get something we could integrate. Questions?
So on the test you said we're able to use the graphing calculator to like see what the graph actually looks like?
If you want. I mean, I'm not quite sure that really helps. I just wanted us to see what we were doing. We had a curve. We looked at it between 1 and 2, and we want to know how long that was. Okay?
Do you want us to recognize property of logs to get it in its final form?
To that, if you had 1/2 natural log 2, I wouldn't take off.
And when we first did like where we squared f prime,
Yes.
and then we had it under the square root and started taking the integral,
Uh-huh.
Would it have been incorrect to add the two, add two of the fractions and then get that answer and add the left fraction? You know what I mean? Like if we had done the 1/2 plus 1/4 x squared and I added those and then I added that.
Oh, do them like separately?
Yeah.
Yeah, that would have been fine.
Okay.
As long as you get a common denominator, as long as you turn to one fraction, something over something, as opposed to fractions that are separated with addition and subtraction.
Okay.
Yeah, because in that integral you had 3 terms, 1, 2, 3. And when we put them together, we wound up with one term, one numerator, one denominator. That's what you need. Okay, let's do a different one. All right, so this is x equals y to the 4th over 8 plus 1 over 4y squared. Sorry, anyone else need this? Which one did you just take? That was from last class. Where's the stack? Did that get around? Okay, they're right there. Okay, so we have, again, because this is arc length, we have 2 different formulas to choose from, right? This one is solved for x, right? So we're going to be looking at this as like a g of y. Oh, I forgot to give you the limits. Sorry. Y is between 1 and 2. And we want to find the length. Should we look at it? Why not, right? What I like about this Desmos graphing thing is that if you want to graph something that's like x equals instead of y equals, all you have to do is type in x equals and then just type in the function. Y to the 4th over 8 plus 1 over 4y squared. So look at the curve. It's weird, right? A weird looking curve. It's definitely not a function of x, right? Fails the vertical line test, but it is a function of y, right? Lines drawn this way only hit the graph once. So we want to look at this graph between y equals 1 and 2, right? Y equals 1 and 2. So when we look at y equals 1 and 2, our y is up and down, right? So that means here, and then here's 2, here. So we're talking about this part of the curve right there, right? So we've got our x and our y-axes like this. So that's what we're looking for. What is the length of that little piece, that little arc? All right, so I said we had 2 choices. Since this one is g of y, we're going to be using integral, that the length will be the integral from c to d, right? Instead, that's what's on your formula sheet. Then square root of 1 plus, yeah, I'm just making sure I'm using the same notation. Did I put the square? Where's the, yeah, I did it in brackets, okay. So g prime of y squared, and then it'll be with respect to y, right?
Yep.
So when I'm done with all this, I should have just y's in there, right? So I can integrate with respect to y. So let's take our derivative. What is g prime? I think I'm going to erase this. You got the idea here, right? Okay. G prime of y is what? 1/2 y cubed. Now for this one, I would have looked at that as being 1/4 times y to the negative 2. That's what I would have done before I took the derivative. And then I would have dropped the negative 2 down, right? And that would have given you negative 1/2 y to the what? Negative 3, because you're subtracting 1, right? Now on the last problem when I squared, didn't I just do this times itself next to one another?
Yes.
I'm going to do this one a little different just to show you there's different ways to do this, all right? Instead of just writing it and like foiling it out, first I'm going to rewrite this derivative. I recognize that I have a 1/2 in both terms, so I factor a 1/2 out, okay? And then I have y cubed minus y to the negative 3, right? I'm going to write that as 1 over y cubed. That's the same thing, right? I'm going to get a common denominator between these two now. See, I'm not squaring it yet, right? But I know I'm going to need to square it, so I'm putting it together as a fraction now. This is going to be 1/2, and then what would happen? I have to look at this as being over 1, y cubed on top and bottom. So y to the 6th, then minus this over y cubed. Okay, so that is my derivative written a different way, yes? And now if I square this, if you don't like what I'm doing right here, you can just do what we did on the last one. I just want to show you something different. So if I square this, think about what happens here. If I take this and square it, because that's multiplication, I square the 1/2, then I square this, right? So when I square the 1/2, I get 1/4. And then when I square this fraction, I can square the top and square the bottom separately, right? Because it's a fraction. When you square a fraction, you just square numerator and denominator. So what's y cubed squared? Y to the 6th, right? Okay. And what am I supposed to do with that? Add 1, right? I'm supposed to add 1 to that, aren't I? Let me do one more thing on this derivative. Let me write it as y to the 6th minus 1 squared over, how about just 4y to the 6th? Is that okay? Instead of having the 1/4 out here, I'm just going to put the 4 down here on the bottom. So let's add 1 to this. So if I do 1 plus this squared, so this is kind of a separate little idea here. If I add 1 to this, I'm just going to have plus 1 out here, right? But I'm going to want to put those together with a common denominator. So when I write my 1, I'm actually going to write it as 4y to the 6th over 4y to the 6th plus y to the 6th minus 1 squared over 4y to the 6th. Y'all following me? I'm kind of like thinking ahead that this 1 needs to be this so that I can put those together. And now let's put them together. So that part right there, is equal to, let's see, what's my new numerator? It's going to be this plus this, right? I'm going to expand this out. I'm going to multiply this. I'm going to square it, okay? So I'm assuming on the side you could do that and square it out, right? Yes? Is that enough? I can assume that. 4y to the 6th, we're about to find out. Plus what? What would that be squared? Y to the 12th minus 2 y's to the 6th plus 1. All over your common denominator, 4y to the 6th. Do you see anything that we can clean up there? Yeah, 4y to the 6th and this 2y to the 6th go together to give you just 2 of them, right? Positive? Yes? So watch like this. Goodbye. Right? That's what happens there. Okay, that's the thing that's going to go under the root. Are we happy to see that?
Yeah.
Yeah, this up here now, factors. So it looks again like a perfect square trinomial, but it's not, but because of the 12th power, but it acts the same way as a quadratic does. So I'm ready now. Let's go to the integral. The length of that curve is the integral from 1 to 2 of the square root of this thing up here, but I'm going to factor it, y to the 6th plus 1 squared. That's it factored. And then over the denominator, which is 4y to the 6th dy.
So should we always try to like shoot for that?
Like a perfect square trinomial? Is that what you're talking about?
Like something that we can just take the square root of top and bottom separately.
I think when you see the problem, when you actually do this derivative and start putting the 1 plus together, you'll start to see that it's leading you that way. But there are some problems where you don't have to actually do all this. Like it'll work out a little cleaner. We're going to do some more today where you'll see that this part right here is not it's not this, so we don't do the same thing.
Okay.
But be ready for it, like look for it, because it's coming, all right? Yeah, it's coming. All right, so this is integral 1 to 2. And y to the 6th plus 1 over 4y, not 4y to the 6th, over what? 2y to the 3rd. I forgot to take the square root. dy. There we go. So we do root on top and bottom. And now I can split that into two terms again. Right? I can do y to the 6th over 2y cubed, and then I can do the other one. So let's see where we would be here. Integral 1 to 2. And what's that? 1/2 y cubed would be the first one. That's this over this. And then the next one, I'm going to do plus 1/2. And then I just have a y cubed down on the bottom. I'm going to write as y to the -3 on top. dy. And I'm doing it that way because I'm going to do power rule when I integrate. I'm done. ... You can do the rest, right? All right, that's it. Yes. Oh, is this? Yes. Read through the instructions on your own. If you have any questions, email me or text me. Okay. All right, we're going to move on. New idea now, all right? We are now moving into the next section, 7.5. So this is surface area. And I didn't state this. I didn't state this on the notes I just handed to you. So you might want to add this to the surface area of revolutions. Because surface area is a very general idea, but we're actually going to go back to what we had done before. Remember when we were taking functions and wrapping them around different axes? We were finding the volumes, weren't we? So we've already looked at if we have some function between a and b, some function of x here, that if we want to find the volume, if we wrap it around the x-axis, okay? If we go around the x-axis, so that's our axis of rotation, that the volume of that is dun, 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 pi integral a to b it's the outer radius squared minus the inner radius squared. So if we're going from here to here, then the inner radius is 0. So it's just that function squared. Now, I've been putting brackets around that, right, and squaring. But if I put 2 here, it means the same thing. That means squaring it, all right? Just don't put the 2 here, because then sometimes people will think that you mean square that x, and it can get confusing. So dx, right? That's the formula for the volume of that if I asked you to wrap it around the x-axis. And if we wrap that around the x-axis, let's go ahead and just imagine I did that. Here's kind of a picture of what it would look like, roughly, right? We have our axis of rotation would go through the middle of that. That's what it would look like if we wrap that. Agree? So we know we could calculate the volume of that. But now what we want to know is the surface area. And when I say surface area, I'm talking about a different type of measurement, right? Volume is like if you have a bucket, volume is how much water you can pour into it, right? Surface area is like the amount of paint that you would need to paint the surface of it. So when I'm looking at this, if I am talking about surface area, what I'm talking about is this outside, right? Just this outside of this thing, all the way around. I'm not talking about, there's no end cap here, okay? This is not a solid anymore. Don't look at it as a solid. Look at it as just like a shell. Does that make sense? Yes? Okay. So we want to know the surface area of that. So let's see how we might be able to come up with a formula for that. And we're going to do something we've already done many times in this class. We've come over to our graph. We've got this idea that we've used of doing like this infinitesimally thin rectangle, right? This time, what I want us to do is take this little arc, you see that little red arc right there? And I want us just to take that little infinitesimal arc and wrap it around the x-axis. And what would that look like if I wrap that little arc around the x-axis? It would look like, I don't know, something like this. Sorry, I messed up the bottom of that. I really messed up the bottom of that. Try that again. There we go. That's better. Yes.
So on the arc length part, we never use DS. Are you gonna like?
We're about to.
Oh.
Yep. I only pointed that out there for what we're about to do.
Oh.
Yep. The question was, we haven't talked, why did I tell you that those two things were equivalent to DS? Here we go. All right? Okay. So, if I wrap that little red, just this little red piece around the x-axis, I get this, right? Now, I'm not wrapping a rectangle. I'm not wrapping the rectangle around the x-axis. If I wrap the rectangle around the x-axis, I get this washer, right? This thing that has thickness to it, has volume, right? This does not have, it's not solid. Like I can put my hand through this, right? My arms, I can stick my arms through this. It's like a rubber band, right? Basically, it's like a rubber band. Right, agree? Okay, so on this rubber band, if I could somehow come up with a formula for the area of that rubber band, then all I'd have to do is add up all the areas of the rubber, all the different rubber bands, right? So same thing we've done before. If we could find a formula for just that area wrapped around, I use the integral to add them all up, right? Move left to right and just add them. So we need to find the area of that rubber band. So we come in here and we cut it, right? We'll scissors and we lay it out flat. And when we lay that rubber band out flat, we get something that looks like this, right? Now we're talking about area now, not volume. Area, so it's two-dimensional. All we need to know to find the area of this is like length times width or length times height or however you want to look at it, right? So do we know any of the measurements of that thing? I heard two, I think I heard the same, I couldn't tell. What did you say? D what? D what? Okay, so the width of this rubber band, right, how thick it is, we have to be real careful. dx was the width of our rectangle, wasn't it? dx. But I'm taking the arc and wrapping it. The arc is not dx. What is it? ds. That's what you said, right? It's ds. It's this right here is no longer the width of the rectangle. It's actually the length of this little curved segment, which is the arc length, which is ds. So this right here is ds. Do y'all see that?
So they just notate it differently, just to show that
It's not dx though.
yeah.
Remember, ds is the square root of 1 plus the derivative squared, right? That's what that is. Yes.
So would it be like any width of, like, does it necessarily have to be just that? Like, could it be like another arc within that same graph?
I'm not quite sure I understand what you're saying.
Like, it's the same thing like that, but like, let's say we take another arc, but like further down,
Uh-huh.
before we reach B.
Yeah.
So then, like, if we took that, would that also be ds, like the width?
It's always ds because the formula for ds involves x, doesn't it? So as you move down, x is changing, right? And so when you're at a different x, your ds is going to be different also.
Okay, but it'll still be ds.
It's still ds.
Okay.
You're asking a very good question, okay? Look, this formula right here, the value of this right here depends on x, right? And since this rubber band was made by just choosing some arbitrary value of x between a and b, that little arc, that little piece right there is going to be this computation, right? But since it depends on x, if instead I move my piece down here and do this arc, that arc's going to be different. But we can call all of those little pieces ds. We're calling them ds. They all depend on x though. Okay, so it varies as you move, the ds changes.
Okay, I mean, I know this is gonna be like a weird question, but would it also be the same if it's on the y-axis as well?
Yes, but our formula is going to change.
Oh,
Our formula is going to change a little bit.
But will it still be ds as? Like,
Yes.
Okay.
Yes, it still will be. Because ds doesn't care if your function is a function of x or a function of y. It doesn't care.
It's just the end formula that's gonna change.
Yeah. Because we only have one piece of this, right? Didn't I say we need to find a formula for the area of this?
Right.
We only have one piece. We still need to find this piece. And that's, that we did talk about that before when we were doing shells, that we had this circle here. Now it's just the rubber band, right? Not the whole thing. But if we take this and cut it and open it up, then we're actually talking about the circumference of that, right? So in order to know the circumference of this, you need to know the radius of that, right, r? But the radius of that is exactly what here? For this slice, how high up was this? F of x, right? It's the function's value there. So as you move over, right, that is going to change. So this right here is, what's the formula for circumference? Circumference? 2 pi r, right? So this is 2 pi times the radius, but the radius is f of x. So as you change where you are, okay, your rubber band changes, right? And so if we're here, we have a certain value of the function at that place, and we have a certain ds for that. Then if we move a little more, this changes and that changes. If we move a little more, it changes, right? And all these things, and we're adding them all up. Make sense? The thing I think that bothered me when I was a Cal 2 student is that how can we add all these things up if the function's always changing? Like if the curve is always changing, how is it that this computation somehow keeps track of all those changes that are happening? And that's the absolute beauty of the fundamental theorem of calculus. That if you're doing an integral, definite integral from a to b, the only information you need is the antiderivative. The antiderivative of that function evaluated at 2 endpoints does all of that for you. Amazing. It still blows my mind that all we ever have to do is find the antiderivative, plug in 2 numbers, and it accounts for all the different variations within the curve. It's crazy, but that's the way it is. Okay. Okay. So the area of this little piece is this times this, right? And that would just be one piece. So we want to add them all up. We add them up. We're going to do an integral. So let's look at our formulas that I handed out to you there. Let's see if it makes sense now. So if we take, yes, go ahead, go. These are good questions.
So for the ds and for the 2 pi f of x, will that ever be squared or not?
For the ds and this right here, will it ever be squared?
Or, yeah, like let's say we're trying to find to see that same angle or that same arc, just double. So wouldn't we just square that? Like, would there ever be a problem where we have to square that function?
No.
To find let's say if it's the same ds, but it's higher or lower, or if we want to just find out where it would land if it was 2 times as big.
I think he's referring to other sections that we've done, and he's relating it to that. Is that what you're
Yeah.
I think he's talking about section, like 7.3, are you talking about where it's where you have to add something to the,
To that formula to see if it's if
When
it would ever get bigger.
Yeah, because I'm not following you.
um,
Like if your axis of rotation is in a different place?
Yeah,
it's
but
here
if
if
you
you're
s-
adding
Okay.
or adding subtracting.
We will never tweak this formula, okay? Now, the reason why is because in this class, when we're doing surface areas, we're always going to go around the x-axis or the y-axis and never anything else. We're never going to move our axis of rotation down or up or over here. And that's just because we could, and we could generalize this formula even more, but the book doesn't do it. I'm not going to do it. I mean, we could, but it's just, the main idea here is that we can get surface areas, all right? So this is it. These formulas that are boxed, they're not going to get any more complicated than what you see here, all right? So let's take a look at these formulas because this is a little confusing.
I need your A and B.
Yeah, what? My what? Yes, so on your notes, when I printed this, I had a typo because I did some copy and paste. I think one of these on yours has AB, right? And the other one does not have CD?
Yes.
Take off the AB.
Are we replacing?
We're leaving it blank.
Because it's only the arc length, right? It's not
Pardon?
You don't use ABs because it's not the rectangle you're using, it's specifically the arc length position.
Let me explain. I'm going to get to that. Let me just kind of tell you where we are here. All right, let's say that we have some curve, okay? Let's call it y equals f of x. And we want to wrap this around the x-axis, right? If we want to wrap it around the x-axis, we're going to use this formula right here, right? This formula. This formula is actually two different formulas that you have to choose from. And let me explain why. First, let's understand, the 2 pi was from the formula, right? 2 pi came out, and then it was f of x. F of x is y, isn't it? We've always said f of x equals y. And then ds was the arc length. But remember, ds could be two different things, couldn't it? This could be the square root of 1 plus f prime of x squared dx, or it could be 1 plus the derivative of x squared with respect to y. Do you all agree? Yes or no? Because this is very important. This ds can be two different things. So which one we use will depend on the problem we're given. And I'm going to do an example of each one right now, all right? And then after we do that, we will talk about rotation about the y-axis. All right, so let's start just with this, all right?
So we're doing this, and whenever we get here, we're plugging into our DS.
We're not, yeah, well, yes and no. We're not going to do them as two separate problems. All we're going to do is, let's just do one. Let's just do one, yeah. I think this will become much clearer, hopefully, once I do a problem.
So if it were like a function of y.
Let's just do one. Let's just do it. Look, sometimes the best way to explain something is to actually just do something and see how it works out. All right, so look, let's take this. Y equals square root of 1 plus e to the x. And we're going to be looking at this on the interval where x is between 0 and 1. And we're going to find the surface area. I'm going to put SA for surface area, okay? Find surface area if rotated about the x-axis. Yes?
I guess this goes back to like, that notation of between 0 and 1.
Mm-hmm.
Does it always have to have the equal sign? Would we ever see it without?
That is another good question. Y'all are all full of good questions today. That's good. I like that. You absolutely have to have it. And the reason why is because if you just look at the interval, let's just look at the interval between 0 and 1, right? If we take a measuring stick, right, and measure the length of this, it's going to be 1. If I include the endpoints, the measurement is 1. But if I don't include the endpoints, it's impossible to measure that interval. Like if I take the endpoints off and I say measure the length, it is not like 0.99 or, you know what I'm saying? Like, because there are an infinite number of numbers leading up to 1. Like there's no number right before 1. It's not possible to ever find a number right before 1. Like if you think you found it, I can find one closer to 1 no? This is a pretty tough idea, actually. It's very easy to prove. Let's just say somebody thinks that there's a number that's right next to 1, okay? Let's just say that they think there is. The number that is the closest to 1 that you could ever get. And let's just call that, I don't know, p, okay? Yeah. So you claim that p is the number right next to 1. So I'm going to find one now that's even closer. And all I have to do is take the two and average them. If I take those two numbers, if I take 1 and p and average them, that is a number right between the two. Yes?
So then it'll just get closer to 1, but it just won't hit it, right?
Well, you can't measure a length if you can't ever get to the end of the interval. Like, because you could always go a little bit further, so the arc length would change a little more, and then it would go a little further, and the arc length would change again, or the surface area, whatever it is, it would change. So we have to have a closed interval. You have to.
Because then it'll just be like 0.9, 0.99, 0.9999.
Yeah, you keep on going. Now, you could do a limit, but then if you're going to do the limit, then you may as well just put equals because you're headed towards 1 anyway, right? A lot of people think that this number is the number right next to 1.
But it goes on forever.
Okay, so can I find a number that's, yeah, it's okay that it goes on forever. 0.999 repeating decimal?
Yeah.
I think that's a really good candidate for the number right next to 1, right? Wouldn't you agree? It'd be really hard for me to find something closer. All right, let's call this x. Everyone with me? Let's call that x. What's 10x? If I multiply that by 10, what happens when you multiply something by 10? What happens to the decimal? Moves over, doesn't it? Right, so isn't this 9.99? These 9s keep going, so that's that, right? Okay, now just time out. Come over here real quick. We're back in like basic algebra. What's 10x minus x? 9x, right? Everyone agree with that? Okay, so over here, I'd like for us to do 10x minus x, but I want us to do it vertically. All right, so what would 10x be? 9.99 forever. If I subtract x, which is 0.99 forever, what would you get if you subtract these two? You just get 9, don't you? Because the tails of these kill each other off. So 10x minus x algebraically is what? 9x. But according to this, that would have to be equal to this, which means x would have to be 1. So it actually turns out that 0.999 forever is actually the number 1. That's not the number right next to 1. That is 1. Does that bother you? Okay. So there is no number. Good try. 0.99 is a good try, but it's not the number right next to 1. It is 1.
So then 9 would be like 0.98
Can we just,
forever.
Hard to get? What?
like, very long?
0.98 forever
Yeah.
would not be.
But would that be like closer to 1 instead of it being like 0.99 forever?
0.98 forever?
Yeah.
Okay. Let's get back. We're going to go back. Because we can very easily, we're getting off into, I love the questions, but we have other things to do. I'm sorry. Come by my office. We can talk about it. Anything you want. All right, let's find the surface area if this is rotated about the x-axis. First thing I'm going to do is I'm going to write down the formula that I use when I'm rotating a surface, getting a surface around the x-axis, which is this formula. Integral, 2 pi. Integral, no limits of integration are here yet. All right? And then it's y ds. Yes? Okay. Now, when I look at this, I say to myself, well, this is already solved for y, right? So this is a function of x. This is a function of x. So when I'm looking at this ds part right here, that ds, I had two options, right? I could do two different things. I could do square root of 1 plus f prime, right? Which is really like y prime squared dx, or I could do square root of 1 plus x prime or g squared and then dy. So the question is, which of these is easier, right? Y prime, right? Because it's already solved for y. If I did x prime, I'd have to solve that for x. And then my integral would be with respect to y. Here it's going to be with respect to x. Understand? So I think I'm going to like this one better. So I'm going to rewrite this 2 pi integral. Now, what about my limits of integration? I'm integrating with respect to x, right? So my limits of integration have to be x values. And I'm actually given x values, aren't I? 0 to 1. So I can go 0 to 1 here. Now, what is y? This is critically important. What is y for us? It's the square root of 1 plus e to the x, right? And I need to replace that y with something with x in it, don't I? Because I'm integrating with respect to x. So I can't leave this as y. I've got to replace it. So that's going to become the square root of 1 plus e to the x. Y'all with me? Times ds, and I'm using this one, which is the square root of 1 plus, and then I've got some work to do here, don't I? I need to find the derivative and then square it and plug it in there, right? So I think your question earlier was, are we going to do what we did before? And then kind of, we are going to have to do the arc length in here. We're going to have to do the derivative and square it and plug it in and add one square root. We're going to have to do that, but we also have this to deal with. So it's like we've added a new element we've just added one piece to the arc length formula and a 2 pi. All right? So let's do our derivative over here. What's y prime for us? So derivative of the square root of something is 1 over 2 roots of that something. Now chain rule, derivative what's inside? E to the x. So this is really just e to the x over 2 root 1 plus e to the x. Now I get to do what to it? Square it. Okay, so when I square that, nice things happen. What happens when you square e to the x? You get e to the x squared, that's e to the 2x. And then when I square the bottom, what happens? 4, and then that root goes away. So 4 times, in parentheses, 1 plus e to the x. And I need to add 1 to that, don't I? Now, I'm going to put that, since I already wrote this out, I'm going to go ahead and just slap this in here. E to the 2x over 4 times 1 plus e to the x dx. Everybody okay with where we are? No questions? Now this integral doesn't look that nice, does it? But let's go with the same theme that we had when we were doing arc length, and that's, let's try and clean this up in here. So let's do a common denominator, because that seems to have worked every time we've tried this, right? So if I do a common denominator here, what am I going to get? Maybe I should do that on the side here again. I need to change this 1 into what? This, right? So 4 times 1 plus e to the x over itself. So that'll be here and here, and then I have plus this, e to the 2x, and then over the common. Y'all all right with that? Now what? Let's distribute the 4. Okay? 4 plus 4e to the x plus e to the 2x over 1 plus e to the x. Ah, yeah, that numerator is nice again. It's hiding from you, but it is nice. Let's see, I'll do it over here. So what we have, I'm going to rewrite the numerator. I'm going to flip it. I'm going to go e to the 2x, which is really e to the x squared, plus 4 times e to the x plus 4. So all I've done is rearrange the numerator so that if you squint your eyes just enough, you can see that that's like u squared plus 4u plus 4, and that will factor. And then on the bottom, nothing changes. Do you see what I mean by, like, these problems have to be chosen like perfect for you? Like if this was a 3, right? Like if that number was a 3, none of this would work, all right? So this becomes e to the x plus 2 on top, that quantity squared, over 4 times 1 plus e to the x. Okay, that is what's under this root, right? Right, let's continue the integral then.